The unusual stability of benzene can be determined experimentally by measuring the enthalpy changes that occur on hydrogenation reactions of different cyclic unsaturated compounds. And here we have a look on the hydrogenation of cyclohexene, which is this molecule where we have a 6-membered ring with one carbon-carbon double bond, in comparison to the hydrogenation of cyclohexane, where we have this 6-membered ring and 2 carbon-carbon double bond. And then finally of our benzene molecule, which can also be described as cyclohexane-1,3,5-triene if we use the Kekulé structure. Let's start with the hydrogenation of one carbon-carbon double bond in the cyclohexene molecule. For the hydrogenation, we use hydrogen and a platinum catalyst. And if we measure the change in enthalpy, we see that the change results to a value of minus 120 kilojoule per mole. And this reaction is exothermic, as the newly formed 2 carbon-hydrogen bonds are stronger than the broken carbon-carbon and hydrogen-hydrogen bond. If we now go to the next hydrogenation, the hydrogenation of 2 carbon-carbon double bonds in cyclohexane-1,3-diene, we would expect that we have now a change in enthalpy which is twice as much as we saw for cyclohexene. The reason for this is that we saw the hydrogenation of 1 carbon-carbon double bond, and now we have 2 carbon-carbon double bonds, so we expect a value which is more or less twice as much. And indeed, this is the case, so we can see that the change in enthalpy is minus 232 kilojoule per mole, which is almost the expected value of 240 kilojoule per mole. So when we now go to the hydrogenation of 3 carbon-carbon double bonds in our theoretical Kekulé structure, which we call cyclohexane-1,3,5-triene, and if this principle continues, we would say now we have 3 carbon-carbon double bonds. Hence, we would expect to see a change in enthalpy of minus 360 kilojoule per mole, because this would be the value for the hydrogenation of 3 carbon-carbon double bonds. However, the measured enthalpy change is considerably different. It is only minus 208 kilojoule per mole. And that means that benzene is more stable than the hypothetical Kekulé structure. And this difference in enthalpy here, the 152 kilojoule per mole, are also called resonance energy of benzene. And why do we now see a significantly lower change in enthalpy for the hydrogenation of benzene compared to the expected theoretical value? We can explain this difference in stability with the delocalization of the pi electrons in the benzene ring. So if we have the cyclohexane-1,3,5-triene molecule, then we do not see any interaction between the pi bonds. However, in our real benzene molecule, we know that there is a delocalization of the pi electrons. That means we do not have this alternating carbon-carbon single and carbon-carbon double bond, but instead we have the delocalization of the electrons over the complete ring.